Here we've got a problem where water is flowing through a turbine at a rate of 7.55 cubic feet per second. The pressure at position A is 21.4 psi. The pressure at position B is minus 5 psi. Determine the horsepower delivered to the turbine by the water. And so I've got some given information here. Notice that the flow is in this direction. Notice that the inlet diameter is 12 inches. The outlet pipe inner diameter is 24 inches. We're given the volumetric flow rate. We're going to assume a nominal density of water of 1,000 kilograms per meter cubed. We want to know the power delivered by the turbine, power delivered to the turbine by the water, or the power output from this turbine. Now, this is actually should be somewhat reminiscent of what you had in Thermo 1 in process thermodynamics. We were given in that class, we were given problems where we were given the fluid inlet and outlet temperature and pressure. We would look up the enthalpy, and remember, we would use an energy balance where the work would end up being equal to the delta H, right? Work is equal to delta H. We would assume that there are negligible changes in kinetic energy and potential energy. Usually for turbines, we would assume adiabatic, so there was no heat losses, and that left us with delta H is equal to the shaft work. Here we're only given the pressures, the volumetric flow rate, the pipe diameters, and the height difference. All right, we don't know the temperature. We don't, from this, we can't really calculate the enthalpy. So what we're going to do is we're going to use our process fluidics. All right, we're going to use the Bernoulli equation, and we're going to get the head extracted. So if we remember our Bernoulli equation in its most general form, we have the energy at position 1 plus the energy added minus the energy lost through head losses through friction minus the extracted energy, extracted head, is equal to the energy at position 2. Now in this case, we are going to set position A as 1 and position B as 2. Head added, is there any head that's being added? No, this is a turbine. In this case, we have head extracted, and in this case, this is what we are solving for. Are there any losses? We're not told anything about any kind of losses. There will be some losses, but we are going to neglect those losses. We can set the datum equal to our low position, say at position B. All right, and remember, we usually did not include potential energy changes, but we're going to do that here. Velocity heads. Do we need to include the velocity heads? Well, yes, we will. We have a flow rate, we have a volumetric flow rate, but we have our velocities are going to be different at the inlet and the outlet. All right, so what do we need to do here? Well, let's start assembling some information. We need to calculate the head extracted. Head loss is going to go to 0. Head added is going to go to 0. Z1 and Z2, that's going to be a 3-foot difference there. So we can set Z2 equal to 0. Z1 is going to be 3 feet. What about the pressures? We know the pressures, right? 21.4 minus 5. Rho, we know what rho is, and we know what G is. Also, notice this is not a steam turbine. This is a liquid water turbine. So that's another difference. Usually in thermodynamics, we were dealing with steam turbines, which is usually what you'll find. But sometimes you'll find turbines just running basically like a water wheel with liquid water. So we need to start solving for these terms, and one of the first things that we need to do is we need to deal with the velocity. That's the only thing that we really don't know too much about. And so to do that, we just need to go through and do some area calculations. So we calculate the cross-sectional area at A, calculate the cross-sectional area at B. We know from continuity that the mass flow rate is going to be the same at A and B. We are also assuming that this is an incompressible fluid. So the volumetric flow rate is going to be the same at A and B, and so we can solve for the velocities at A and B. So the velocity is equal to the volumetric flow rate divided by the cross-sectional area. So that's 2.93 meters per second at position A, 0.733 meters per second at position B. Does that make sense? Yes, because it is the velocity should decrease, right? Because the diameter is increasing. Now, the next thing we need to do, so now what that means is we now have the velocities taken care of. Everything should now be accounted for in this Bernoulli equation. So what I've done is I've just taken the Bernoulli equation, solve for the extracted head, and then plug everything in. And we get an extracted head of 65.242 feet. How useful is that? Well, it's an answer, but it's not the final answer that we need. We want the power, right? We want the power, the horsepower. And so remember, head extracted is energy per weight of fluid, right? And so in SI units, again, I prefer to do most of my thinking and working in SI units if I can help it. So energy extracted is joules per Newton. Per weight of fluid is joules per Newton. If we want to calculate the, sorry, that's the head extracted. The energy extracted, we multiply by rho g. And so again, I'm doing these step by step. You don't have to do these step by step, but I'm just doing it for illustration purposes. So we take the head extracted and multiply by rho g, and that we get a joules per meter. And so let's put that as kilojoules. Make it a little easier number to read. So 195 kilojoules per cubic meter. And then if we want to take that energy extracted and multiply it by the volumetric flow rate, we will get a power. And so the power is energy extracted times Q. And so that will be 55.9 horsepower. If we want to convert it to kilowatts, about 41.7 kilowatts. So this is a problem where we finally had a Bernoulli equation problem where we were dealing with the extracted head.